First of all, Barbara and Mikael, thank you very much for the invitation. And hello, everybody. I'm very honored to speak in this lecture series of Bose-Einstein condensation. As Barbara said, the topic of this lecture is Bose-Einstein condensation of photons. That means the quantized particles of light. These are experiments that are done in the weak coupling regime of matter and light. Basically, what the usual configuration is, it's a Bose-Einstein condensate in an optical microcavity filled with dye molecules, but there's also more recent experiments in other groups, as I will talk about, in semiconductor microcavities. To begin with, let me start with this imaging, picking up on basically previous lectures. Bose-Einstein condensation has first been achieved in the gaseous regime in cold atomic gases. That's a cover image of one of the first Bose-Einstein condensates. This particular one is of the Kettle group, with cold gases cooled to the nanokelvin temperature. What one sees then is a phase transition to a state where atoms, as loosely speaking, quantum mechanically speaking, march in locksteps. So it's a macroscopic state. Whether it's a molecule or not, probably this is, well, that's simplified. For sure, it's not a molecule, but this was the cover image of the Science magazine. What happens if you're going, if you're cooling atoms or particles to a Bose-Einstein condensate is the following. While at high temperatures, one has a classical gas. At lower temperatures, atoms show wave properties. The de Broglie wavelength scales as 1 over the velocity, which is proportional as 1 over the square root of temperature. And if you go so low that the thermal de Broglie wave packets spatially overlap, then for bosonic particles, you get you find Bose-Einstein condensation. That is a condensation into the ground state. At still lower temperatures, one has a pure Bose-Einstein condensate. This is a typical series of time of flight images when one cools through the phase transition. So here you see the ground state emerging. There's over 100 experiments in the world. This particular one is of our group. We are also, in my group, we are also doing cold atoms, but that's not the topic of today's talk. But there are over 100 experiments in the world. Bose-Einstein condensation has been proposed by Einstein, building on preliminary work on the quantum statistics of integer spin particles by boson in 1924. And it has been experimentally realized 1905 with dilute rubidium and sodium atoms by these 3 gentlemen, Cornell, Wyman, and Kettle, for which they were awarded the Nobel Prize in Physics 2001. This was, well, basically the topic of previous lectures. If you cool, in summary, if you cool down atoms to very low temperatures, you obtain Bose-Einstein condensate. But now what happens if you're trying to do the same experiment, just cooling down in 3 dimensions for photons? So what happens is the following. Photons just go away. It's getting dark. This is not a very interesting state of the light field. The background is photons normally have no chemical potential. They're not conserved particle. The blackbody radiation of at 0 Kelvin is the absence of photons. So that's not a very interesting state of the light field. How can you do better? The first work that was related to photon Bose-Einstein condensate, to my knowledge, is by Seldovich and Levich, 2 Russian physicists in 1969, who proposed to scatter photons of electrons at thermal equilibrium in a plasma. So the expectation from this paper was that one then should get a shockwave structure that resembles a BEC. This was never observed experimentally. What does work experimentally is, of course, Bose-Einstein condensation of exciton-polaritons, which operate under strong coupling, also in parentheses, half matter, half light, and they're basically what one does, one addresses excitons to the photons, and the material particle of the polaritons, as you heard in the first Candela lecture, then is responsible to allow for thermalization. So this works experimentally, and this is today a wide field also. What is more close to the work that I will be talking about is a proposal for photon fluid in a nonlinear resonator by Ray Chow. So what he suggested is to obtain a photon fluid that is thermalized by photon scattering, very similar to atom scattering or polariton scattering in polariton or atom BEC experiments. Of course, in free space, in vacuum, the cross-section for that is basically zero. So his idea was to put an atomic gas to enhance this probability. The cross-section, nevertheless, was too low to obtain thermalization, but I still think that this is a very nice proposal. So that's the outline of my talk. So I will be talking about experiments where one obtains a matter-like dispersion relation in an optical microcavity, and thermalization of the photon gas is achieved by absorption and re-emission events on dye molecules in this cavity. I will first talk about the thermodynamics of the system and then on Bose-Einstein condensation. So all these first experiments, they're basically in the first half of this talk before the break. And I will talk about some applications. And subsequently, after the break, I will talk about more recent experiments, which is with this system, which is a non-Hermitian phase transition for such a photon condensate, and applying variable potentials for cavity photons and what one can do with that. Okay, so to begin regarding the system, as I've been mentioning, we used an optical microcavity, as is also done in polariton physics, to modify the photon dispersion. In our case, it's a curved mirror microcavity, and the spacing between mirrors is very small, so it's an integer number n times half the wavelengths. And for the sake of simplicity, let's now assume n is equal to 1. Then it's very clear that very long wavelengths do not fit into the microresonator due to the boundary conditions. We need a zero of the field here and here. There's a maximum wavelength or minimum frequency of the light to fit inside. So we have a low frequency cutoff, similar as in a microwave waveguide, which in this case is for the TM00 mode of the n equal to 1 longitudinal mode manifold. And on top of that, it's a higher transverse modes. And here at some point, n equal to 2, the n equal to 2 manifold would set in. So the dispersion relation is not anymore linear as in free space. There's this low frequency cutoff, and on top of that, the dispersion turns out to be parabolic. So next, we reach thermal equilibrium of the photon gas by absorption and re-emission events of these dye molecules, as I will explain on the next slide. So we fill dye molecules in liquid solution inside. So that's these are spectra of a perylene dimid, which is a typical dye that we use. And you see here both the absorption and the fluorescence spectra. There's a Stokes shift in between. In particular, between the fluorescence and the absorption probability, it turns out there's a Boltzmann-like scaling, e to the minus h bar omega divided by kBt, the photon energy divided by the thermal energy. And this follows from detailed balance. As I will talk about in a few minutes. And now, if that is fulfilled, it makes sense that the photons acquire a thermalized state. This makes physically sense, and one can also show it because the asymptotic state turns out to be a Bose-Einstein distribution. But what's the background of that relation? Well, this is my simple model of a dimolecule with an electronic ground state and an electronically excited state. And on top of that, it's all these row vibrational states. And now it turns out that every 10 to minus 14 seconds or so, a solvent molecule collides with a dye. And this leads to a thermalization, not just within the ground state manifold, but also within the electronically excited state manifold, because all electronic processes are much slower than this rapid collisions. They are at a scale of nanoseconds and not of 10 to minus 14 seconds or so. So we get a thermalized distribution, both in ground and excited states, and the thermalization also imprints onto the spectra. That's the background of this Boltzmann-like scaling between emission and absorption. You find that if you mathematically add up the corresponding excitation and emission amplitudes from each of the substates. Of course, it makes physically sense, as I've been mentioning. And the temperature that comes into play is the internal row vibrational temperature of the dye, which of course equals the kinetic temperature. And in our case, this is at room temperature. So what happens if you absorb a high-frequency photon before it emits? It relaxes to a lower row vibrational state, and you get a Stokes shift of the photon. If there's more and more of such Stokes shifts in free space, you run out of resonance, and the thermalization stops. But in the microcavity, as I've been mentioning, there's a low-frequency cutoff, and one gets a thermalized state on top of the cutoff. So in the microcavity, the longitudinal mode number is fixed, and we thermalize the two transversal degrees of freedom. We have a two-dimensional photon gas that couples to a heat bath. The dye molecules act as a heat bath at room temperature. So in these next 5 slides, let me talk in more detail about the thermalization process. So what thermal equilibrium means, of course, is that every microstate of a system occurs with a statistical weight determined by its Boltzmann factor. But an alternative equivalent point of view is that it's detailed balance, so that the rates from a state of the light field I to J divided by the reverse is related to this Boltzmann factor. So basically a higher energetic state because of the rates will be populated less likely. What this now means, what we need from the dye solution such that this is fulfilled is the following. So we absorb a photon of frequency omega and emit a frequency of omega plus delta omega. This changes, as you see here, the population numbers of the light field configuration I and J. So here you get a photon less at frequency omega, and at omega plus delta omega, you have 1 photon more. And for what we need for the transition rates between those two configurations, that's written down here. So this is the ratio of the photon numbers. As in general, the rates as the Einstein B coefficients times the number of photons times absorption and emission. This factor here cancels. So we find basically that you just have the absorption at frequency omega and the emission at frequency omega plus delta omega divided by the reverse. What this means is that we require that alpha from omega times the rest at frequency omega plus delta omega divided by alpha omega plus delta omega by f omega is this Boltzmann type scaling. If we solve that for the temperature, that is the exponential factor, well, we can check whether a particular dye fulfills or can serve to thermalize the photon gas is by calculating the spectral temperature of that, which is given by basically this formula here, assuming that the spacing delta omega is relatively small. Now the question is that fulfilled for different dyes? If you look, for example, for perylene dimid, you find that the spectral temperature is relatively constant. So there are variations of 10, 20%, but this is that's still relatively small, and these it's also hard to measure. So this might well also be measurement inaccuracy. However, inaccuracies. If you look for coumarine, however, which is a dye that has a relatively small quantum efficiency, only 40%, you find that this is not at all fulfilled. It really goes up to 2000 kelvins or so, the spectral temperature. And the reason why it's not fulfilled here is that it's incomplete thermalization, and the quantum efficiency is low, and so there can be processes that violate this Kennard-Stefanov relation. So basically, as if one thinks more carefully about it, one finds that if one has a thermalization process and has a quantum efficiency of unity, the dye or the thermalization medium must fulfill the Kennard-Stefanov relation ideally. So essentially, you want a dye or a solid semiconductor medium with a high quantum efficiency. And the next question now is, then you can expect to thermalize the photon gas. The next question, of course, is do you vary the photon number during the thermalization? In Planck's blackbody radiation, there's processes like the thermal excitation and the emission of photon, and this combined photon process creates a photon. Of course, also the opposite happens, and that destroys a photon, and that's precisely why in the blackbody radiator, the photons just go away as you cool down. In this new scheme, we have a low-frequency cutoff, and there's quantized electronic levels of the dye at about 2 electron volts at the energy of a visible spectral range photons. And because of that, thermal excitation is suppressed by a factor e to the minus h bar omega cutoff divided by kBt, which gives you a very small number, 10 to the minus 36 or so. And because of that, every time you see an emission of a photon, you basically know for sure that there must have been an absorption process before. And during the thermalization, the energy varies, but the average number is conserved. So if you want, you can call this a white wall box for photons. And on this next slide, I want to convince you that the trapping of photons in such a dye microcavity is formally relatively similar than atom trapping in a cold atom apparatus. The numbers are completely different. I already told you that we have a quadratic dispersion, but now let's work that out in detail. So the energy of photons is h bar c kz squared plus kr squared. Kz is the wave vector along the cavity axis. And in paraxial approximation, so if kz is much larger than kr, you find that it's h bar c kz plus kr squared divided by 2 kz. So we do get a quadratic term. And if we now it turns out that the wave vector along the cavity axis is conserved during the thermalization because that's tied to the low frequency cutoff. Because of that, we can set this first term, h bar z kz, to an effective mass times c square. So this basically determines the kz. And if you insert that into the second term, you see that the second term looks like a kinetic energy. And that's the kinetic energy of photons moving transversely in the resonator plane. So next, it turns out that we also have a trapping potential from the mirror curvature. The background is if photons move to the side, away from the center, then due to the curvature of the mirrors, the spacing appears smaller than in the center. So to fulfill the boundary conditions, we need shorter wavelength that is higher energetic photons. In thermal equilibrium, photons are not very happy with that, so they rather remain in the center, and we imprint a trapping potential to the photons. So with that, the system becomes formally equivalent to two-dimensional gas of massive photons that's harmonically confined. And this is, well, the expression of the energy. So the first term, as I've been mentioning, it's associated with a frozen longitudinal motion. The second term is the kinetic energy of photons moving transversely. And the third term now is from the trapping potential imprinted by the mirror curvature. And for spherically curved mirrors, this is harmonic. So for such a system, it's known that from Bagnato and Kleppner that in thermodynamic equilibrium, one has a Bose-Einstein condensates if one puts sufficient particles. The critical particle number is pi squared divided by 3 times kBt over h bar omega. Omega is the vibrational frequency squared. And if you put in numbers at the room temperature, you arrive at 77,000. So, which is a reasonable number. So why is that you can expect to get a BEC at room temperature, whereas in dilute atomic gases, you have to cool to the nanokelvin regime? The reason is that the effective mass is very small. It's a visible, the energy of a visible spectral range, photons, so about 2 electron volts in mass units, where you arrive at a few times 10 to the minus 36 kilograms, or 10 orders of magnitude smaller than the mass of the rubidium atom. And because of that, the vibrational frequency is high, and we can make the ratio kBt over h bar omega to be a reasonable number, even at room temperature. So this is how such an experiment can in principle look like. So this is our difilled microcavity. And in principle, we should be able to couple a spectrally broad pump inside. And what we should get out is a spectrally sharp BC peak plus a broad thermalized cloud. And the nice thing is that the free energy of such a state of the light, filled with both the spectrally sharp BEC peak plus the thermal cloud, is lower in the microcavity than this broad pump. That's in principle normal BEC physics, but that's very nice. Now, how do we do that experimentally? So in our experiment, so this is our scheme of our difilled microcavity. The spacing between mirrors is not lambda over 2, but 7 times lambda over 2, but that works as well, provided the free spectral range is much larger than the line width, which is of order of the thermal energy, which is fulfilled. And we do not pump with a broadband source, but with a laser, which is narrowband. And we analyze the light that leaks out of the microcavity, both spatially with a camera and spectrally with a spectrometer. And well, this is a photo of the heart of the experiment, the microcavity. So these are the mirror surfaces. And we pump, so here is the cavity axis, and we pump at 45 degrees. And these prisms are such that the pumping radiation can transmit through. So the spacing between mirrors here is a millimeter or so, which is much larger than when we operate the experiment, but otherwise you wouldn't be able to see through. So to operate the experiment, we reduce the spacing to about a micron, and we put a drop of liquid dye in between, and that holds by adhesion. This is now experimental data, first in the regime much below the onset of BEC to probe whether we have thermalization. Here's the cavity low frequency cutoff, and to the left, it's lower wavelengths, that is higher photon energy. And on top, you see experimental data now recorded at room temperature. And you see that the data fits quite well to a thermal distribution. That's basically a Boltzmann distribution. And the largest deviation is peak here at 532, which is from residual pump radiation. If we increase the temperature of the apparatus to 365 kelvins or about 90 degrees Celsius, so the dashed line still is a room temperature 9. And what you see is that the spectral intensity at the low wavelength, high energy side increases by about an order of magnitude. In this regime, much below the onset of a BEC, we can neglect this factor -1 in the Bose-Einstein distribution. And what the chemical potential does, it basically acts as a normalization factor. You can draw that out of the exponential. From the output power, that is the integrated spectral intensity, we can determine this normalization factor, which enters in the exponential. And in both cases, we find a chemical potential that's different from 0 and strongly negative. And we interpret this as evidence for two-dimensional photon gas with non-vanishing chemical potential. So what you see here is now a spatial image of the microcavity emission. So what we did, we just directed a camera to the microcavity emission. And basically, the low energy photons near the cutoffs are more in the center, and the high energy photons, so the high part of the thermal cloud is more outside, and everything is confined to the center by the trapping potential imprinted from the mirror curvature. So normally we pump in the center, but now what happens if we, to test things, do not pump in the center, but more outside? What you of course expect is that due to the thermalization, photons are dragged in the center. And this is now experimental data probing that. And what you see here is the position of the pump beam where we pump. Here's the trap center. On the y-axis, you see the position within the microcavity where the maximum of the fluorescence is emitted. And what you see is that provided that we remain within a capture range of ±60 microns, indeed, the fluorescence comes out in the trap center as would be expected from thermalization. So this is basically what was sketched in the cover of Nature Physics, where this experiment was published in 2010. And more recently, we then tested whether we can have a BEC. Subsequently, for that, we had to increase the output power and to put more photons. And we indeed see a peak in the center that we attribute to the BEC, in addition to the thermal cloud. So basically, what happens if, other than a black body radiator, the photons do not go away when we cool, in general, cooling and an increase of the density does the same. So in the case of the light bulb, photons just go away. But in this case, here we increase the photon number. We see a peak in the center, which corresponds to the BEC. So to investigate things in more detail, we looked at spectra. So up here, these are theory spectra, and these are experimental spectra. What you see is that at low photon numbers, we basically see a Boltzmann cloud above the cutoff. So this is the same that I showed you previously. To the left, again, it's lower wavelengths, that is higher photon energies. And if you put more photons, we in addition see a peak at the position of the cutoff that we attribute to the BEC. That's wider than theoretically expected due to the finite resolution of our spectrometer. photon number where the BEC sets in is at about, well, the power is about 1.5 watts, and the photon number is 63,000, with which experimental accuracy agrees with the expected value. So this was published in 2010. And there's more recent photon BECs at Imperial College by Rob Nyman in Utrecht. Jan Kleers now in Twente has his own group, and in several other laboratories. There also is a plasmonic Bose-Einstein condensate by Javier Thomas. She uses dimolecules to thermalize, and related experiments are light condensation in multimode fibers. So there's actually a more recent experiment, as I've been mentioning, also observing photon condensates in semiconductor microcavities. This is very interesting because this is a VCSEL-like geometry. Corresponding experiments have been carried out at Imperial College by Rupert Olden and colleagues, and in Wrocław, so very near to Warsaw, by Maciej Pieska. What those two experiments see is a Bose-Einstein condensate in a setup that's very close to those used in VCSELs, which of course is $1 billion per year market. So actually, in your iPhone, you have a laser that's relatively, from the apparatus, is relatively close to what one can realize a Bose-Einstein condensate with. And that's, I think, truly exciting. And these experiments operate at room temperature. While the difference to polariton condensation, or the way that the experiment works, the difference is that one operates at room temperature and plus, some other modifications. And the thermalization there does not occur by polariton collisions, but rather from absorption and re-emission events on the semiconductor material. And this relates these experiments now to other coherent optical emitters. First of all, polaritons. So polaritons, as I've been mentioning, operate in the strong coupling regime of matter and light. And depending whether you have thermalization or not, you either have a polariton BEC or polariton laser. So as lasers, the photon condensation works in recoupling regime of matter and light. This is why it's photons. And to get a BEC, in general, thermalization has to be much faster than loss. If that is fulfilled, and one has a well-defined ground state, one obtains a photon BEC, whereas in the usual laser case, one has no thermalization at all, or at least less thermalization than the loss rate. And what is interesting is that on that scale, old bulk semiconductor lasers, they weren't thermalized, but on this scale, they're a little bit further on the right-hand side. The background is that to understand their spectra, one has to account for the so-called Rosenbrock-Shockley relation, which precisely is the Kennard-Stefanov relation, just its different event, as one is for dimolecules and the other one is for semiconductor systems, but that's the same thing. So this modifies the spectra, and historically the development went more from industry, went more to the left-hand side, because what people did, they increased the output power, the outcoupling rate to increase the output power. And so the industry development went more to the non-equilibrium case. And the recent experiments on Bose-Einstein condensates, they basically managed to draw that back, and so far back that one really, to the right-hand side, that one really also has a BEC for these semiconductor systems. Okay, we of course wanted to look experimentally whether we can see such a crossover from lasing to Bose-Einstein condensation. This is now corresponding experimental streak camera data. First, for low thermal contact, that means in a regime where we do not have thermalization to achieve, or almost no thermalization to achieve that, we put the cavity cutoff to 596 nanometer, which is relatively far away from the absorption maximum of the dye, so that we do not have absorption and re-emission events almost. To remove the initial state further from the equilibrium state, we didn't pump in the center of the trapping potential imprinted by the mirror curvature, but more on the side. And what you see then is that the light oscillates back and forth in the trapping potential with time. So this is a highly non-equilibrium lasing-like state, in this case, a mode-lock lasing state. On the other hand, if we put the cutoff to 570 nanometers or 571, there, well, we're much closer to the absorption resonance, and we do have absorption and re-emission events and thermalization of photons. There you see that photons thermalize in the trap center to the lowest energy state in the microcavity, and there we do get a Bose-Einstein condensate. So this basically shows the transition between a lasing and Bose-Einstein condensate, which is an issue on thermalization, whether thermalization is faster or slower than photonless. So next, I will talk about measurements of spatial correlations of the microcavity emission, basically to test whether we can see macroscopic coherence. First, I will talk about experiments where we took corresponding data in the thermal regime. For that, we directed the output of the microcavity through a Michelson interferometer, where one of the two mirrors is replaced by a cat eye retroreflector. So this is a experimental configuration that has been used previously in polariton experiments, and this allows one to relatively nice analyze such correlations. And what you see here is that the fringe visibility, so these are interference pattern, and as function of transverse position, one can determine the fringe visibility with this camera. And what you see here is, and in this way, measure the first order correlation function. And you see that this fits can be relatively nice. This is experimental data. This can be relatively nicely fitted with an exponential, a Gaussian, proportional to the radius square divided by the thermal wavelengths. And this way we can determine the thermal wavelengths, which is 1.48 microns. This builds upon earlier work studying the transverse coherence lengths in optical quantum gas, first for polaritons, where the coherence length is determined by the cavity line width, and then by the group of Robert Nyman, who studied such photon BECs in a non-equilibrium regime. And here on the right-hand side, you see the variation of the thermal wavelengths with temperature, so which scales as expected. So basically, as we increase the temperature of the apparatus, the thermal wavelengths decreases, becomes shorter. So next, we checked whether at higher phase space density can obtain long-range order. And there you see the variation of the transverse coherence lengths with photon number divided by the critical photon number. And you see that we basically see at the point when the spatial de Broglie wavelengths overlap. So if the phase space density increases beyond about 3.3, then we see macroscopic coherence emerging, and this extends very rapidly over the whole system size. And here on the right-hand side, you see in more detail mapping out the correlations near the phase transitions, which, while there's a long regime where it scales almost linear, the visibility with distance. As the last slide in this first half, a further property of such condensates that it's a grand canonical condensate. Regarding the background, usual Bose-Einstein condensates, for example, cold atoms and polaritons, operate in the microcanonical ensemble. That means the particle number is relatively fixed. One can nevertheless have fluctuations in the condensate because there can be fluctuations of the condensate part against the thermal cloud. But those are relatively small. They are only Poissonian, and one gets, well, in the ideal regime at least, a G2, a second-order correlation function at 0 times of 1. The grand canonical ensemble is defined as a system where one has exchange of a system with a reservoir. Interestingly, one can have that for such microcavity photon condensates because the way that we thermalize, that's by absorption and re-emission on dye molecules, and one can write that as a photochemical reaction where one goes back and forth between, well, absorbing a photon and emitting photon, which converts simultaneously a ground state dye molecule into excited state dye molecules and vice versa. And this is precisely the situation that we can write as a system of photons that's coupled to a reservoir with which not just energy but also photon number is excitation number is exchanged. And for most cases, it doesn't. For most issues, it doesn't matter very much whether you treat a problem in the canonical or in the grand canonical regime. But there's one exemption that is the fluctuations of particles in the Bose-Einstein condensate, because in the grand canonical regime, there's actually huge fluctuations of the particle number, and the fluctuations can be even as large as the average particle number. So if the reservoir is large, and the second order correlation at 0 times can be 2 and not 1. So same in the condensed state as in the thermal state. So effectively what happens at a large reservoir is that the square root of n fluctuations of the reservoir mix into the system if the reservoir is sufficiently large. And normally, if you just let's say have a bucket of helium and say part of this bucket of helium is a system, then one does not expect that because then there's only diffusive exchange between the system and the reservoir. And this is not fast enough. That has been noted by Ziff, Uhlenbeck, and Kack in a review long ago, 1977. So they calculated that, but they were not very careful because in the abstract they wrote, a case is made that the grand canonical ensemble doesn't represent a physical system in the condensed state. But what they did not consider is this case of a direct exchange between two different species where one can have internal conversion. And this is faster. And in this case, one can have a grand canonical condensate. And this is now corresponding experiments, that's the last slide that I will show. So first, this is experimental data now in the canonical regime, where we have still relatively small fluctuations, so G2 of 0 of about 1.01. But if the condensate becomes smaller, then relatively to the photon number, the dye molecules is large enough such that the square root of n fluctuations of the reservoir mix into the system. And there, at a photon number of, well, 3,700, you see that we get a G2 of 0 of almost to 1.93. So we have huge fluctuations which are as large as the average number. And this influences not just the second order correlation, but also the first order correlations. Here you see more and more phase jumps in a beat signal with a frequency stable laser. The background of that is if we get a zero intensity, then the condensate has to restart, and it can restart with a new phase.
So now we will start asking you the questions from our audience, and we thank you all for submitting your interesting questions. So we start from the beginning. The first question is, I wonder what dyes and solvents can be used in the experiment. What properties should an ideal dye/solvent exhibit?
Yeah, right. So basically, the dye should have a high quantum efficiency, and the concentration of the dye should be so low that one is not in the strong coupling regime. That's basically what it is. Yeah. Of course, the hard part is that you just have a micron of spacing, because you have to put the two mirrors very close together. So we need very good mirrors to nevertheless, in this 1 micron, after many round trips, have reabsorption, several absorption and re-emission events. So basically, our cavity finesse is about 100,000. And then within a millimeter or so, or a few millimeters space, which is, I don't know, 6,000 cycles or something like, where the light goes back and forth, then we have reabsorption, and we have several reabsorption emission events.
Okay, and the question was, maybe you have some examples of what these dyes could
Yeah,
be?
right. So PDI works, rhodamine works, and a typical solvent is ethylene glycol or acetone.
Okay, and some perovskites probably as well now. For example,
We didn't try. Would be interesting. Yes, I mean, maybe you can help on that. Barbara can help on
that's,
that.
bouncing the idea back to Basia.
Yeah.
Okay, so that was one question. Another
He's
one
the
is,
expert in that. Yeah.
another one is, do photon BECs exhibit long-range phase coherence similar to atomic BECs? If so, how is it measured experimentally, and are there key differences in coherence properties due to the nature of thermalization in the dye medium?
Yeah, I mean, this basically shows, I mean, transversal coherence, I showed you before, it has transversal coherence, but it also has I mean, basically, the long range coherence, if you're in the canonical regime, we do have long range coherence. And also longitudinal coherence. But if you're in the grand canonical regime, the long-range coherence reduces due to these frequent intensity jumps. So basically, it has a tunable first and second order coherence.
Okay, thank you. Third question, is there a photonic analog of the Gross-Pitayevsky equation?
Yes, one can write down the Gross-Pitayevsky equation, but of course the interaction is very weak. We are now thinking of engineering interactions with Xi2 processes, two subsequent Xi2 processes with a Xi2 nonlinear medium. By applying that 2 times, then hopefully we can engineer the stronger interactions. But otherwise, well, and interestingly, weak, I will talk about that a little bit, weak losses can also lead to an imaginary two-particle interaction. That has been pointed out by Michael Wouters.
Okay, thank you. Another question. So there is no need to make BECs by cooling photons, just like MOT, or evaporating cooling for atoms, isn't it?
No, there's no need. Even at room temperature, one cannot have a Bose-Einstein condensation. Yes.
I guess that's the whole point, to have it in the room temperature. And another question exactly in the same spirit. So is it realistic to put the cavity back into a cryogenic environment and then create a BEC in it?
Sure, it would be possible, yes, yeah. I mean, one has to have a reason to do that. If it works at room temperature, one has to have a reason to go to the cryogenic environment, yeah. Which I'm not sure. Maybe one could try, yeah. But one has to think about that, whether it makes sense. But it can be done, sure.
Okay, and the last question, what would be the wave function analog for photons?
The wave function analog, it's precisely the same as for material particles in the two-dimensional plane. So basically, the third dimension, we need to provide a low frequency cutoff and to get a non-vanishing effective mass. But in the two transverse dimensions, it looks precisely as for material particles, just with this effective mass that corresponds to well, that's the low frequency cutoff in mass units.
Okay, thank you very much. That was the last question. And so I think we should just go back to the remaining half of the lecture.
Okay. Okay. Yes. So right. So so in this first half. So thank you. In this first half, I showed basically how the system is realized and some properties of photon condensates in optical dimicrocavities. I will now, in this subsequent second half, talk about more recent experiments, non-Hermitian phase transition, and applying variable potentials. So let me directly start with a non-Hermitian phase transition. What is important there is, again, the grand canonical system properties. I've been talking to you, well, that because we thermalize by absorption, the photon gas by absorption and re-emission on dimolecules, which is shown here on this photochemical reaction, we have a system of photons that's coupled to a reservoir of dimolecules. And this leads to, if the reservoir is large, then basically the square root of n fluctuations of the reservoir mixed into the system size. All this was in the absence of losses. But now, if you do look into things in more detail, one finds that I mean, losses as in any optical systems do play a role. We do have losses, for example, due to mirror transmission, and to compensate for these losses, we also have to pump. And the influence of losses has also been pointed out a lot in polariton physics. Where one sees the influence of those losses experimentally, if you look into more detail into the second order correlation functions, because what we see then is an oscillatory behavior. And the question is, what is the origin of this oscillatory behavior? That you see here. So it doesn't go just from a non-vanishing value down smoothly to 1, but there's an oscillatory behavior. The background of that are losses. Just in general, what losses do in a system, in a Hamiltonian system, they break hermiticity, so the system Hamiltonian becomes complex. And an interesting property of such non-Hermitian systems is that exceptional points emerge, and this here shows you generally the eigenvalues as a function of two parameters in the case. So there are two solutions, and there can be, in the case that an exceptional point occurs. So basically, when these two solutions planes cross, then the eigenvalues coalesce. That means they really become the same, and it just becomes one eigenvalue. And this is called an exceptional point. There has been earlier work in the field of laser physics in polariton traps. Exceptional points have been realized, and there's been a theory for a phase transition between a photon laser and a polariton BEC that has a non-Hermitian character by Peter Littlewood and colleagues. And the question that I'm asking here, whether we can have such exceptional points in a photon BEC. And first to point out that this is at relatively weak loss. So what you see here are observed microcavity spectra. So the solid lines, colored lines, is experimental data, and the black line is equilibrium theory at room temperature. And on this scale, you do not see a difference. The background is that we have separated timescales. So the loss timescale is about 3 orders of magnitude longer than the thermalization timescale. But the interesting point is that pumping and loss do nevertheless break time reversal symmetry a little bit, but this is sufficient that non-Hermitian system properties arise, but to detect them, we cannot do so with first-order correlation experiments on the scale of our experimental accuracy, but the second-order coherence can serve as a sensitive probe. Well, you saw these oscillations, but how do this precisely emerge? Well, for that, we have to think about the fluctuation dynamics around the stationary state. For that, let's look at the coupled equation of dynamics for the photon number and the excitation number x, which is the sum of the photon number plus the excitation number, the number of dimolecules. So if we would have perfect equilibrium, then the sum of the number of photons and di-excitation would be constant. But because we have losses, then also x can change, and this here shows you the corresponding deviation. Basically, well, here you see the loss timescale, so that's a non-Hermitian matrix, and delta is a damping, and omega 0 is an oscillation frequency, which becomes non-vanishing if we have a loss term. Actually, this oscillation frequency that actually it comes from, it's also known, the mathematics is relatively similar to the relaxation oscillations that are known from laser physics. This also arises from precisely the same thing, that if you have losses, the whole coupled equations of motion become nonlinear, and this is why such a non-Hermitian matrix arises. And here in this case, the dynamics is driven by the grand canonical statistical fluctuations, and the phase diagram in a simplified way that arises is as follows. So at very large losses, one has a crossover to lasing, and below that, if the oscillation frequency is larger than the damping, we have an oscillatory BEC phase. That's the one I showed you. And now if you go to smaller and smaller losses, we expect when the loss equals the oscillation frequency, we expect an exceptional point. So this is when the system is critically damped. And below that, we have a bi-exponential BEC phase. So that's basically if the damping is larger than the oscillation frequency. We, of course, wanted to look at this by exponential phase, and we see that here at a smaller photon number, there you see that our experimental correlation data is well fitted by exponential function. We also, of course, wanted to look at the phase transition, and what you see here is the two loss time scales that we see for small photon numbers. And here is the exceptional point at the vertical red dashed lines. And above this exceptional points, we see a non-vanishing oscillation frequency. And we attribute this as evidence for non-Hermitian phase transition at this point between this bi-exponential and the oscillating phase that occurs at this exceptional point. And here you see a more detailed version of the phase diagram as a function of both the mirror loss and the average photon number. So here's the oscillation frequency, and here the oscillating, second order coherence, and here's the bi-exponential phase. And in this, with this data here, we investigated this regime that's shown here in blue. So what happens at the non-Hermitian phase transition is the following. We always have two system eigenvalues, in the oscillatory regime, the split off in the imaginary plane, in the bi-exponential regime, we also have a gap, but that's in the real plane. And at the exceptional point, the two eigenvalues coalesce and the gap closes. And at this point, the system becomes very critically dependent on fluctuations that will rapidly either go into the bi-exponential or into the oscillating phase, and that's what you expect at the phase transition. So to explore the phase diagram in more detail, it's actually to change the loss is not so easy, because then we need different mirrors. But what is relatively easy to change is the dye concentration and the position of the low frequency cutoff. And there what we do vary is a scaled loss, which is basically this term here. And if we now plot the same phase diagram that I just showed you in scaled units and take data for different dye concentrations and cutoffs, we can also map out the phase diagram. So the red points correspond to data here in the oscillatory regime, and the violet ones in the bi-exponential regime. And you see that in this way we can map out the phase diagram. And what is more, we can also show the phase the time scales along the vertical directions, because which is a scaled loss. As you see here, there one sees that at very large loss there would be a crossover to lasing. There you again see this phase transition, and what one sees there is that the phase transition separates by exponential phase from both the intermediate oscillating BEC phase and lasing. And what is interesting here is that the bi-exponential, normally one has just a crossover between lasing and condensation. But in this grand canonical system, there's a true boundary between a condensate phase, also the bi-exponential phase, and these two other regimes. So you can argue that the bi-exponential regime, BEC regime, is something truly different than lasing. So in my final few minutes, I will talk about experiments on generating variable potentials for light in such cavities. First, regarding the motivation, which is strongly correlated quantum gases and quantum simulation. There's many proposals, mainly on lattices, and also experimental work in the field of polariton physics. So to create such potentials, one can use mirror shaping, as I've been talking about for the case of a single trap. With parabolic mirrors, we can generate a harmonic trapping potential. This is a normal configuration where we look at Bose-Einstein condensates. Similarly, would be possible also for example, for double well potential, which we could realize if we can shape mirrors such that there are two corrugations. So because at these points where there is a larger distance between mirror surfaces, longer wavelengths photons fit inside, and they have lower energy, and this corresponds to an attractive potential. And to realize that, such shaped mirrors, which is something technically non-trivial. What we do is the following. We ask our mirror coaters to put a dielectric silicon layer between on top of the substrate, and only then we ask them to put the dielectric coating. What one then can do is the following. One can focus a laser, a so-called heating laser beam prior to operation of the microcavity onto the silicon layer. And what we see is that for a high intensity, the dielectric mirrors a little bit detach. So we can delaminate them at the corresponding position. The interesting thing is that the reflectivity, nevertheless, is essentially unchanged. And by positioning the heating laser beam at different positions, we can create variable potentials for the light field in microcavities. And the interesting thing is that in this microcavities system, the thermalization of a photon gas can proceed in the presence of variable potentials because we cool or thermalize with respect to a reservoir the dye molecules. The question that we were interested in, whether we can, so the motivation was whether one can create interesting ground state ensembles by cooling alone. And examples are, for example, the helium atom. I mean, the ground state of the helium atoms, that's an entangled state for the electron wave functions. Similarly, I mean, a superconductor is or fractional quantum Hall systems. Those are very interesting entangled electron states, which are the Laughlin states. And the way these are being created in solid state physics is by, well, for the case of the fractional quantum Hall system, one puts a strong magnetic field and then one just cools the system. And so by cooling alone, if the Hamiltonian is correspondingly, you can create such interesting states. And this was the motivation for this experiment. So how far we presently are is, well, we can just make single particle states also this shows you an example of a double well potential that we create with mirror delamination. This is a double well potential. This is our silicon layer, and we basically heat up here, down here, and then the middle. So in this way, we can create a double well, and on top of the double well, there's a harmonic trapping potential, such there's a suitable density of states that a BC can be realized. And the two lowest state of the double well are the plus and the minus states. So basically, the ground state is at the photons in the left state, plus those in the right state, and the excited state is, well, minus sign in between. And on the right-hand side, you see corresponding experimental data. So these are images showing the photon energy versus space along the double well axis. And this is the symmetric ground state, and this is the antisymmetric first excited state. And here you see the higher energetic harmonic oscillator states. And if you put sufficient photons that we do get a BC, you see that we macroscopically populate the ground states, and we get a BEC in a split state of light, and this is coherently split of state of light, as you see if we see because we see fringes when we combine the two paths. That means essentially what we realize is a thermodynamic beam splitter. Because when we populate the low energy state, which is a correct superposition. Okay, we more recently extended that to a four-side quantum ring. So basically a ring with four sides. Again, this was superimposed by a harmonic Trapez potential to be able to realize a BEC. And there we can condense in the ground state wave function with no phase winding, and the phase is stable, as you again see by if you look at the interference pattern. So finally, I will talk about experiments where we realize a BEC in a box potential and then measure the compressibility of this photon gas. Box potentials are something that have been investigated in polariton traps also. So here we do it for the photon gas. Let's talk about that first. There has been also work on box potentials by the Imperial group. So at low photon numbers, we essentially fill up this box potential with a thermal photon gas. If we go to higher photon numbers, we get a BC like state in the ground state. I mean, the ground state is basically a sine square. That's a very simple elementary quantum mechanics problem of a particle in a box. And you also see that the momentum wave function, once we have a macroscopic occupation, then that of course becomes very narrow. And here you see that if we put more photons, we essentially see a saturation of the thermal photon cloud, and then the ground state becomes macroscopically occupied. There is it looks like a condensate, but it's a Bose-Einstein, it's a finite size effect. So it looks, it cannot really distinguish from a Bose-Einstein condensate, but on a strictly theory picture, you cannot do the extrapolation to infinity, but it is essentially like a Bose-Einstein condensate. So the advantage of this box system is that you can tilt one of the mirrors and apply a spatially uniform force, which is a great thing to measure the compressibility. We there see for thermal gas, the influence of the small tilt is relatively small, but as we become quantum degenerate, you see that photons much simpler go to the minimum of the potential. The background is if you just occupy the lowest energy state, I mean, this is localized very much on the right-hand side, and because you then populate low energy state, things become compressed much more easily. So from such data, we can determine the compressibility of this photon gas as a function of the density. And this goes down with density, as one expects for a classical gas, as long as we remain below the onset of quantum degeneracy. And as this is reached and this spatial de Broglie wavelengths overlap, then Bose-Einstein statistics sets in, and we do populate low energy energetic states. Then it becomes again easier to compress, and the compressibility increases, and it increases up to the point that we reach the limits of the local density approximation that is used here. And we can also determine the equation of state, which you see here as a function of the chemical potential of this optical quantum gas. So to conclude, I told you about the thermalization of a two-dimensional photon gas and a BEC of photons in this di-microcavity systems. I've been speaking about more recent experiments of observing a non-Hermitian phase transition, and this is interesting because there is a state of the light field, this bi-exponential state, that's separated by a true phase transition from lasing plus the intermediate oscillating state, but what is important to lasing. And finally, I've been talking about the measurement of the compressibility. So in future, with these photon gases, it would be very nice to use that for the concentration of diffuse sunlight. So direct sunlight you can concentrate with a lens on a small size photodetector. But if the sun moves, then you have to move your lens. And on a cloudy day, a lens won't help you because light then comes from different directions. But if you have thermalization in a trapping potential, then also for photons that come from different directions, one expects to be able to spatially concentrate them to the center. I do not know whether there's a practical way for solar light collection, but at least it's an extremely nice concept. Next, I would argue that photon Bose-Einstein condensates are a new state of the light field, and some future directions are to look into the grand canonical regime in more detail to check for superfluidity. So we know it's a Bose-Einstein condensate, but there's no evidence for superfluidity so far. And next, it would be very interesting to study quantum many-body states and periodic potential in more detail. The background is if you, in addition, have interactions, as one can engineer, for example, by splitting photons and doubling again to get an effective Xi2, then the ground state can be very interesting entangled states, and one could cool that directly or thermalize that directly into entangled many-body states, and this is something for cold atoms. You cannot do that because you first have to prepare the state outside of the lattice potential, then adiabatically ramp into the lattice. You cannot directly cool in the lattice. And finally, Bose-Einstein condensation presumably could be interesting for light sources in U wavelength regime as coherent UV sources, because you don't have to invert the system as you do have in a laser, and one can retrap fluorescence. And if one succeeds to realize such Bose-Einstein condensates, vacuum ultraviolet UV sources, a possible application would be semiconductor lithography. So finally, I want to thank the members of my group and also the groups of Hans Grohr and Achim Roche, whom I collaborated with in the experiments for non-Hermitian phase transition and this coherent splitting of a BEC. And I want to thank you for listening.
Oh, thank you, Martin. That was an amazing, amazing lecture. We got some questions, but maybe we'll have more of them in a second. Yeah, so I encourage you, everyone, to type in their questions in the Q&A section below. So I think we go straight to it. Maybe let's start with the first question. Hope that people will input more questions in the meantime. Does the trap potential cause some first-order correlations for n lower than nc?
First-order correlations. It's actually it's too shallow. We would have to cool more. The temperature is too high. So for the temperatures we have now, it does not change the first-order correlations. But basically, Bose-Einstein condensation is a way to populate the ground states. So the regime we are in now, we only see a change of the first-order correlation if we cool to below TC, because the height of the trapping potential in temperature units is just 3 kelvins or so. So at room temperature, we wouldn't see it. But if you have a BC, we populate low energy states, and then we do see an influence.
Okay, thank you. We have a second question. Lattices for atoms are realized optically. Are there any clues on how to realize them for photon BECs?
Oh, yes. I mean, we did, no, we realized potentials and yeah, so the best way to do that probably is by mirror shaping. As I've been talking about, basically to So with this method, but by delaminating, and if you delaminate at different positions, you can do so. I mean, there's also other techniques. One can, with a MBE machine, also structure mirror surfaces and then coat. That's another way.
Right, so utilizing the crystalline structure of the mirror itself.
Yes, yeah, that is also a way. Yeah, the challenge is to reach sufficient precision such that the states are all aligned. That's the challenge, and there one has to be careful. But that's enough. But that's possible.
Okay. Okay.
And how large do you think the lattice could be realized? What are the limits for the cell?
Right. The limits is right. Also Julian Schmidt, who well, former collaborator who now went to get his own group in Heidelberg. He's been realizing 8 sites, 16 sites. There's also a technique in Kaiserslautern, actually, with a 3D printing. Presumably, I mean, right, the advantage with 3D printing is that you can make smaller lattices. So just with what we with this technique can realize is 8 microns distance between the sides. But with this 3D printing, you can make the sides closer together, just 1 or 2 microns. And the good thing there is that the tunnel coupling increases to a terahertz or so, and then it's not so important that you precisely have them on the same level. So with that technique, 100 or 1,000 lattice sites, I think, should be possible.
Wow, so he 3D printed the entire kind of the gain medium in between the mirrors?
Yes, yeah. I think to make truly big lattices is this 3D printing method would be probably the better way. Yeah.
Oh, that's crazy. Okay, I think we've reached the end of this lecture. Thank you very much, Martin, again for this fantastic addition to this series, and also thanks to Basia for helping with the Q&A session.